Welcome everyone today to our first Optimism and Innovation talk titled Creativity and Communication in Science. Today we are joined by Associate Professor Tamar Greaves of RMIT University. Tam leads a research group which is developing new solvents and doing fundamental science on understanding how solvents interact with proteins and cells. Today Tam will share with us her journey and her career of science, as well as sharing what most valuable skills are required of a scientist in the 21st century.
So thanks first to the organisers for giving me this opportunity to present about my research and my career path in science. I really appreciate this. So here we have a collection of what looks like random photos, but it's a summary of my research. And today I'm going to take you through my background, how I've ended up in research, and how I've ended up in research that combines chicken, egg, jellyfish, robots, neural networks, and using these to try and solve some really big problems. And this all involves physics, chemistry, biochemistry, and data science. So a bit more about me. I'm an academic at RMIT. I'm an associate professor in physics. My laboratory is in chemistry, and I'm currently trying to understand protein-solvent interactions. So as a quick outline of how I got here, well, I studied physics, chemistry, and maths at high school in Roopna. Then I went to university at Monash. I've always really enjoyed the mixture of maths and chemistry and physics, and got pretty good grades in high school. So my high school advisors tried to get me to do medicine based on my grades, but I wasn't interested in being a doctor. What I really wanted to do was something in science, but I had no idea what a career in science was. So I did my undergrad and then thought, well, I'll stay on and do honours because I'm liking the science. I still had no idea what I wanted to do. And so I was looking around and going, well, I'll do a PhD. Gives me more time to think, and starting to think that I might like this research. So I had a look at chemistry, physics, and astrophysics, which was my three majors. I decided I didn't have enough programming and I couldn't see there being enough career pathways in astrophysics. So that narrowed it down to chemistry and physics. And I ended up going with physics because the department was more friendly. Chemistry was fine, but I really fitted into the physics department. So I stayed on to do a PhD. And then during that time, I decided that, hey, actually, I really like research and I'd like to do a career in science. And from there, I moved a short distance from Monash to CSI Row. It's about 200 metres, and started a postdoctoral fellowship. So I was then able to sort of start my career as a researcher within someone else's group. Stayed at CSI Row for nearly 10 years, going from a postdoctoral fellow to a research scientist, working on a range of projects, but in a related to field to what I'm still doing. I then moved to RMIT about 6 years ago, and now have my own research group. And I'll be discussing mostly what I've been doing at RMIT during this presentation. So in my past, my PhD was on a technique called Mossbauer spectroscopy, and in it I was firing gamma radiation at clay minerals and trying to see the different structure within them. My research since then has been in very different fields, and I'd like to sort of a take-home message here that as a scientist, it's really one of the fun parts is to be able to move from one field to another field. And each time you do that, you drag a lot of the skills and expertise that you have and use that to look at different problems. So I'm going to start with more about sort of the general thing of being a scientist and my past, and then I'm going to talk about the research. We all have a picture in our head of the science stereotype. And I'm not going to go here on the gendered pathway, but that's obviously there. But we often picture a scientist as either the mad professor wearing a lab coat with lots of chemicals and no social skills. But the reality is really, really different for most scientists. For most scientists to actually be successful in today's scientific community, you really need to have the less visible, what we often call soft skills. You need to be able to communicate and collaborate and work well with others. You need to actually be able to do the administrative tasks and get things in on time. You also need to be creative. And I don't think this gets told enough in high school and even in undergrad, that science is really creative. At its heart, what we're doing every day is going, I wonder what if, and asking questions about things that have never been done before, collecting data and doing new approaches. It's all the time is very creative. We also need to be creative in how we're presenting our data. Can we get people to understand better by making a picture in a different way, by presenting the graph using different methods, by trying different techniques? And sometimes it's directly really creative and artistic. And on this slide are 3 cover art images that my groups had for different research. And this is like really artistic representations of the research that we've covered in that paper. So other things that are perhaps not on the stereotype is our communication. And this isn't just talking, it's emailing, it's teaching students, presenting at conferences, marketing my research, writing papers, everything. Like most of my days are spent communicating in some way or another, whether it's teaching or telling about my findings or doing paperwork. Also travel. This is perhaps getting more well known that scientists often get to travel a lot. I have lost track of how many work trips I, in a non-COVID world, would normally do 1 or 2 international trips a year. I've gone to at least 9 different countries, and some of these are for conferences or doing research, also send students overseas, and have lots of really great trips and interactions with people all around the world. And teaching. So even as an academic, I spend most of my time on research, but I also spend a large amount of my time teaching. And this is either directly as lecturing and taking tutorials, also mentoring and supervising undergraduate students and my PhD students. So it's a lot of teaching either on very core basic physics or on very in-depth data analysis, a whole range of different things. I really love that. And it's fun. So I think that's something that's really important to get across. Science can be really fun. We have days where nothing works, we have days where it's frustrating, but overall, it's actually a really fun career path. You get to work with other scientists, you get to travel, you get to come up with your own ideas for what you're going to do. That said, it still is a bit crazy with how many different things you have to be doing as well as that. And it gives us expertise in a whole range of things beyond just our science. We have to learn about our very core science and our equations and our underlying fundamental theories, but also critical thinking, our communication and our collaboration. And these skills can be transferred to different fields. So people I went to university with, well, one's working at the nuclear reactor in Sydney, one's a couple of working in research overseas, some in the finance institutes, insurance, taxation, lots of things where you need to be able to be good with modeling numbers, using numbers, critical thinking, and applying that in a range of different areas. So I probably covered this a bit about what I like about being a scientist. Well, one of the main ones is I get to work with other scientists, and you get to work with people who think similarly. Part of that is I don't have to worry too much about my appearance. I don't have to worry about the makeup or the high heels. I can tell really lame science jokes and my colleagues will get it, which is also pretty good. I like all the data analysis and the teaching and the travel. And that's an example. Click. This is me last year presenting at probably the main conference for my field. It was in Beijing, and it was a really big audience. So this is one where I was quite nervous, but it was a great opportunity to like really market and showcase what my research group is doing. So my research group, so I have, as of today, 15 people in it, and it changes constantly when I have new undergraduates come in for a semester, PhD students start, PhD finish, and so on. So the number's constantly changing, but as of today, 15 people. There are 2 postdoctoral fellows, so these have finished their PhDs and are now working and developing their own career as independent scientists. Got 7 PhD students, 3 honours students, and 3 third year, so undergraduate students working with me for a project. Each of these people has at least 1 other supervisor, so it starts being kind of a convoluted web with multiple projects, multiple people, multiple supervisors. So I also spend a lot of my time on project management and making sure everyone's making good progress and understanding what their area is. One of my students also, she has 2 supervisors at RMIT and also another supervisor in France. So she gets to spend normally some of each year in France and some in Australia, and she'll end up with a PhD from both institutes. So mainly just wanting to show that my research group and my research is not just one little silo. It's really interactive and collaborative across many countries and many research groups within Australia. So what do I actually study? So now I'm going to start talking a bit about my research area. Well, my research covers many different topics, but they're all connected by one class of solvents. And if you're thinking what a solvent is, it can be something like water or an alcohol or an oil. It's a liquid where we can use it to dissolve other things or use a liquid in some way. Well, my solvents are liquid salts. And the most common salt that you'd be familiar with is table salt, which is sodium chloride. And you can think of it as sodium chloride little balls that pack together really well, and they can form this really nice structured array. That means that they like forming a crystal, and it's why our salt has nice little crystal grains, because these atoms can all pack really well together. For my solvents, they're liquid salts. And what we do is we take it, instead of having these nice, easy to pack balls, we add tails and we add weird little groups on them so that they can't pack together well. And what that means is it makes it really hard for them to pack. So you have to lower them to much lower temperatures before they can form a solid. The benefit is that then they're liquid at room temperatures. So we have something that's like our table salt, but it's a liquid. And so we can use it as a solvent. It's not a salt dissolved in water. It just is a salt that's also a liquid. These are really cool for many, many different properties, but perhaps one of the most unusual is that if we leave out a container of them on the bench, they won't evaporate. So in some ways, they can be considered as green solvents. So if we use them for chemical reactions, we don't have all these organic vapors coming off and being harmful. And there are pros and there are cons to using them. One other one, so because they don't evaporate, we can use them in niche markets. So one application they've been looked at for is as lubricants in space. So you don't have to worry about them evaporating out into a vacuum. You can use them as lubricant and they'll stay there. They also have, some of them are really good for proteins and cells. And that's what I'm going to be talking about today. But one thing that's also really good about them is that there are many, many, many possible combinations. What we're doing is we're taking something that's positive and something that's negative and combining them. And we can make tiny changes to the chemical structure of either our positive or our negative group and have a big effect on the properties of our overall liquid salt. And we don't really know how many possible combinations there are, but we're guessing there's something like at least 1 million, probably a lot more. So huge possibilities to make small changes to their structure and tailor their properties. And well, why am I looking at them? Well, I'm really interested in using them with biological molecules, so with proteins and with cells, and using them to try to solve some big problems that are out there. And this is just a snapshot of a few. So my research is very, very fundamental, but I then work with others who have problems where I can bring in my liquid salts to try to help them and solve the problems, or to just to understand the interactions a bit more to help them. So potential applications are in cryopreservation. Currently, there's very few cells that we can actually cryopreserve and freeze without damage. And our liquid salts are one possibility where we can help solve that. We can use them to improve fluorescent biomarkers. So this is where our jellyfish come in. The fluorescent protein from jellyfish is a really good biomarker, natural, can be reproduced in the labs, and potentially has increased fluorescence when we put it in our liquid salts. Biocatalysis is a really big area. So here we can use our enzymes, which are little proteins that act as a chemical factory. They often take less energy and are less harmful than using traditional chemical pathways. But often we have a lot of difficulty finding a solvent where we can dissolve the enzymes and dissolve the things we want to react. And the ionic liquids have a lot of potential in that way because we can tailor them to be able to do both of those tasks. Also using them, developing new ways for protein crystallization. This is really key because our pharmaceutical drugs often target what are called membrane proteins. Very few membrane proteins have ever been crystallized because they don't like water. It's really hard to get them to crystallize. We're thinking we might be able to design our ionic liquids to provide a matrix where we can crystallize these proteins. And lastly, also for protein extraction, and I'm working with groups in Brazil and Portugal on this. So doing things like getting fungi to make high-end chemicals and then be able to use our ionic liquids to extract them out of this soupy broth And it's a way to make these chemicals without needing to use petrochemicals. So what's actually going on? Well, here I've made up a representation of one question that we're posing in the group and trying to answer. So just to sort of to explain the diagram as the starting point, I've got my ionic liquid, the liquid salt, shown by the red and the green blobs. So we've got our positive and negative, and these are making up our liquid salt. And we've got some water present, shown as a blue circle. So if we were to have a beaker of our ionic liquid, it would have all three components floating around, and we assume evenly mixed. If I then take a protein, and our protein is shown by the squiggly thing up the top, pose the question, is that protein going to go somewhere where it's mostly water, or somewhere where it's mostly the anions or the cations, or an even distribution? So what's actually going to solvate it? What are the actual atom-to-atom interactions that are going to happen between the ionic liquid and the protein? And this is actually a really critical fundamental science, so that we can then design our cation and anions, our positive and negative parts of the liquid salt, so that they're either not damaging the protein or that they're actually benefiting it in some way. But first of all, we need to know what's actually happening. And these are all the questions that are then around that of just, where is it? Well, what does it mean to actually dissolve something? That's quite fundamental. We need to actually make a hole in our solvent. We need to be able to put it in there. We have bonds that then rearrange. So each little tiny bit of this problem becomes more and more complicated. And so I have multiple students working on these questions in different ways, and with either looking at very specific interactions of one small system, or looking at heaps and heaps of different samples to try to figure out what's going on. And the other part of what I do is I showed a robot on the first page. I use what's called high throughput methods, and high throughput doesn't really have any really set definition. But it's kind of a philosophy. So instead of just making up one possible sample, characterizing it, getting the data, make up the next sample, characterizing it, getting the data, is using methods to either select which compositions you're going to make and cover a broad compositional space, or use screening methods. So perhaps just adding in a dye, and if there's a color change, you then screen it and only use those samples for the next step. Using robots to make the samples, using what are called plate readers. So instead of characterizing one sample, you characterize 100 at the same time. These sort of approaches. And why do we need them for our ionic liquids, for our liquid salts? Well, if you remember, I mentioned that when we take out our liquid salt, there's perhaps more than 1 million possible combinations of our cation and anion, of our positive and negative group. But we might use more than one ionic liquid. So we now have a much bigger compositional space, and we might add in some water or a different solvent, and our solute, which in this case might be a protein, and many different concentrations. And hopefully you can see it's gone from being a huge space to an absolutely gigantic possible combinational space, multi-dimensions, and really hard to make up, you know, a meaningfully large set of samples. And so that a lot of what I'm trying to do is develop new methods for how we can do this. And it's been a mixture of robots, really fast characterization screens, choosing what methods we use so that it's a combination of really fast and then also in-depth characterization. And more recently, getting into using data analysis methods for machine learning, so neural networks, to then be able to characterize our data, which is across all these multiple dimensions. And just as an example, if we just take 10 cations, so 10 positive groups, and 10 anions, which are negative groups for our liquid salts, and perhaps 10 different water concentrations and 10 proteins, each one of them is not that many, but that's already making 10,000 combinations. And while my PhD students are really, really good, I don't think they'd want to spend however many years that would be for just one experiment doing it 10,000 times. So touching on the high throughput, I probably covered this mostly, but for our high throughput, the conventional approach is to take a cation and anion, make that up and characterize it rigorously and then repeat. For our high throughput, well, we initially design what our compositional space will be. So we select everything to start with. We then might use different mathematical algorithms to select exactly which compositions we'll make, as opposed to making up absolutely everything possible. Use our robots to make the samples, and I'll show you some pictures of our robot later. Screen the samples. So what I often describe to new students is high throughput is not being attached to your samples. You might have made up 100 samples, but you might screen them and find that only 10 are actually interesting. You've got to throw away those other 90. And that can be a bit hard after you spent time making them. So basically it's a way of thinking about the samples differently. And it's just a way so we can get the information that we want more quickly. It's not going for lower quality information. And that's also a really important factor. We still end up with really good high quality data, but just for a lot more samples. So as an example, I'm going to cover how we make our ionic liquids. So we take an acid and a base and we mix them together and we get our liquid salt. And so long as we've chosen our acid and our base correctly, we'll get an ionic liquid. And stuff like that, it's pretty quick. But if you've ever done high school chemistry and you're adding an acid and a base, it's one of those reactions they tell you to be very, very careful with. It's highly exothermic, which means it gives off a lot of heat. And we have to do it really, really slowly. So our synthesis is dropping very slowly the acid into the base to form our liquid salt. And depending on how much we're making, this is usually 2 to 5, maybe 2 to 8 hours, depends on which combination and how much. And it's literally sitting there watching it. So rather painful experiment. We then need to dry it, and just getting the water out of these things is really hard. So there's a bit of trace water in our acid and base, and we've got to remove that to get our dry salt liquid. So we have a variety of different ovens and rotary evaporators and freeze dryers that we use. But typically it's about 3 to 5 days of just drying the sample. And at least then we can put it on and walk away and do something else. But it can cause a bit of a bottleneck because you can only have, for one of our instruments, you can only have one drying at a time in this method. So we need some other ways. We need to go, okay, we can have really fast characterization methods, but if we can't make our ionic liquids fast enough, there's no point. For the high throughput, you've got to have everything faster. Otherwise, it's just what we call shifting the bottleneck. So just for a bit of light entertainment, but this shows a new method and how we can come up with whole, different ranges of science and ways to do things. So this is something that happened quite a few years ago. It's a cartoon drawing of me, thanks to internet, and of a student that was with me for 3 months. And this was a completely different project where we were looking at making conductive polymers while I was still at CSIRO. But the student came up with a really good new method and we're still using it. And the conversation basically went like this. So I wanted him to try 6 acid and 9 base combinations for screening for this conductive polymers for new batteries. And as the student rightfully pointed out, that would be 54 combinations. Yep. Goes, that would take about 6 months to make. Yep. Well, it was a 3-month project. I can see where he's coming from. But gave him the challenge, and as an awesome student, he was like, okay, challenge accepted, and obviously I'm going to have to think about this differently. So instead of doing our method where each sample takes basically a day to make and the rest of the week to dry, which doesn't really work when you've got 54 samples in 3 months, he just did a really quick screen. So he just took 1 drop of each acid and base, mixed them together, and looked at them. And generally for the combinations we're looking at, we either got, it was a liquid, cool, so that's worth following up. It was a solid, well, that's definitely not going to work when we do it more properly. Or we got black gunge where it reacted and kind of decomposed. So that was definitely out as well. And from it, he was able to screen all 54 in about 2 hours and identify that there were only about 5 that were actually of interest. So it was a really awesome screening method, and we're still using it now in the group. So hopefully you've covered We can either make our samples very slowly, one by one. We can screen them. It's a bit coarse, but it kind of works. And lastly, we can use my wonderful robot. So this is the robot being delivered to RMIT a few years ago, and very nerve-wracking having an expensive, very sensitive robot hanging by a crane, but it was the only way we could get it to fit into the building. So this is the inside of the robot. It's a liquid handling robot, and it allows us to basically do synthesis really accurately. Reproducibility is this key for it. And we can heat, we can cool, and we can control everything. So at the heart of it is, it has a needle head. So we have 4 independent needles. So we can add liquids, 4 of them at the same time, to different vials, all of them control for how fast we do it. We can stir all the samples at the same time, everything. So this was the first experiment we did while I was still at CSIRO with their robot. And what would normally be about 3 months work, we were able to do in 48 hours. I've recently had a student make about 40 samples while he was briefly in the lab, and then able to dry them over 3 weeks. And so it would normally take easily more than 20 weeks by hand. So massive saving in time. And the other key advantage is once that he's programmed all these combinations in the robot, he can then make them again at any point in the future. And while they're being made, he can go and do other experiments and doesn't just have to sit there and watch acid go drip, 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 and watch the thermometer and make sure it doesn't get hot. So really, really good advantages, and means that we can go on to doing some more exciting science while it's happening. So back to our proteins. So hopefully by now I've defined that there is a problem with understanding proteins and solvents and how they interact, that we have our liquid salts, and there's heaps and heaps of combinations, and that we need to do some high throughput to be able to combine all of this together. So we're coming back to our central problem. We have our protein, we put it into our soup of cations and anions and water, and we're going, well, we don't know where it's been, and we don't know what's happening to it. So how can we have a look at it? Well, first of all, for what's actually happening. This here is a protein that you'll have seen in real life, but it might look a little bit different. This is our hen egg white. So if you've cooked an egg, you've destroyed the protein called lysozyme. So this is lysozyme, which is hen egg white lysozyme is one we're using. There's other types of lysozyme, but hen egg white lysozyme, one we're using. And the main reason that we use it is it's quite robust, so it's hard to destroy it. It's really cheap, which is great when you're just trying to scope out a whole new field. And it's really well characterized, so we can compare to what's been done before. So on the left, we have our happy protein, which is how it would be sitting in the egg. And as we move across, we've got what's happened when it's what we call denatured. So it's lost its structure. It's becoming unfolded, and it's just losing all of that, what we call secondary structure, and lost all structure. So these sort of changes can be characterized using a range of different techniques. And that's a little bit about what I'll be talking about and what we've had to develop and modify for these techniques to work with our liquid salts. So we're looking at tiny changes. So perhaps as we're going for the first to the second picture, we wanted to be able to see those sort of very small changes in just little tiny parts of the protein structure when we're adding in our liquid salts. We also want to know if any of these massive complete death to the protein structures has changed as well. But this is what we're looking for. So what happens as we cook our egg, and we can destroy this by either making it more acidic, by heating it up, adding different chemicals. All these proteins will die very easily. But what happens is that the proteins go from basically being a ball floating around to the proteins get sort of stretched out and lose structure. If we have multiple proteins present, they then all sort of tangle together, and that's where we get our cooked egg. And it's what's called irreversible. Once you have our cooked egg, can't go back to having our uncooked egg white. So there's also issues about how to maintain that protein in the happy state for long term, against thermal degradation, and for other proteins which are much more sensitive than our egg white. So how do we look at this protein structure? Well, some of these graphs may not look that exciting, but they give us a huge amount of information. So one method we can use is what's called Fourier transform infrared spectroscopy. Basically, we shine different lights from the infrared region, so not visible, infrared region, shine that on our sample, and we see which bits interact with the sample and get absorbed by the sample. And then we see what else goes through it. So peaks are showing the sample absorbed that part of the wavelength. And that gives us information. You can see on this one, that peak is shifting. And that's giving us information about changes in one part within that structure of the protein. So it's telling us if one of these sort of squiggly parts in the protein has changed or been lost, we can see that information from this technique. We're also using small angle X-ray scattering, and we do this at the Australian synchrotron in Clayton. And it's a technique which I particularly love using. So here we fire, we fire X-rays at our sample, and they hit the sample and they scatter. So they, instead of going through as an arrow beam, they come off at very, very tiny angles. And from that scattering, we can get a huge amount of information. So I've just shown a very simple example here, skipping out a whole range of steps as well, but we can get the size. So here we can just model our protein as being a ball, and we can get the radius of it. So the radius of this one is about 1/millionth of a millimeter, and we can measure that accurately and then compare if that's changed as we changed our solvent. We can also see if our line becomes curvy like this, it's also, that then tells us other information. That's saying instead of all having lots of balls all the same size, we now have balls of lots and lots of different sizes, which means that our proteins are aggregating and lumping together, which we don't want. Oh man, wrong button, sorry. Lastly, there's different things that we can do with our X-rays so that we can then model the data to a higher level of accuracy. And so this is something I've been working on in the last 2 years. And this is our jellyfish green fluorescent protein. And for each one, you can see this at a green and a blue pattern. The green is the protein as it would come out from the jellyfish. And then the blue is what's happened when we've added some ionic liquid salts. And we're able to model it from our X-ray data and pick out these tiny changes in exactly which parts are being affected. So it's a really powerful technique. So what have we learnt? So I just want to give a bit of a reflection on how long research takes. So I've been working with ionic liquids since 2005 when I first joined CSIRO. I want to get across that research really, really takes time. It took about 7 years to the point where we sort of had enough expertise in these areas to start thinking about proteins. And it was a new direction. We'd finished up looking at quite a lot of different areas, went, what next? I thought, well, proteins are a great challenge. And it's then taken probably the last 6 years for us to develop a lot of expertise working with proteins. And the first 3 to 4 years is really, really basic of just trying very simple approaches, starting to meet people in that field, build up collaborations, learn the techniques, adapt them to our samples, and see what we can do. And then start asking some really big research questions and start applying what we know to some bigger problems. And scientifically, we have learnt a lot. So we know that the solubility and the stability of our proteins, it really depends on which protein and which ionic liquid, their concentrations, how long we leave the samples for. And I'm not going to go into all the specific detail of, for this protein and this liquid salt, this is what happens. But we've been able to get some, what we call design rules. So we know if we want to stabilize a protein, then this ionic liquid is likely to be good. If we want to have one that's soluble, then we know we definitely won't use anything with an acetate. So we've been able to get some good fundamental information. And now we're starting to look at the very, very specific interactions by using some more advanced techniques. So just as a quick summary, if we take 3 of our liquid salts, and it's a bit of a game of spot the difference. So as I said, small changes to their structure can have a big change on their properties, particularly if you're a protein. So these are 3 completely different ionic liquids. You may notice there's not a lot of difference between them. For one of them, the top one, the protein unfolds. It's a really, really terrible salt to add. In the middle one, it's good. And in the bottom one, the protein won't even dissolve. So this is why we need lots of fundamental research to understand, to go, well, why? I mean, we can do lots of experiments and just map out and just go, yep, this one good, this one bad. But if we want to design it and improve it, then we need to understand the why. And that's what we're really working on now. And lastly, as I mentioned at the start, research is very collaborative. It involves working with lots of people. And we'll see how this slide goes. I just wanted to give a bit of a snapshot of the last few years of the collaborations, how they've developed and how extensive they are, just to show what research is, that it's not just a couple of people working in a lab by themselves. More often it's a picture more like this. So my research started with ionic liquids and understanding their properties. That then led to fundamental work on proteins in these ionic liquids, and that started to be in collaboration with the Australian synchrotron, which is run by ANSTO. More recently by Monash, where they're making, a collaborator there is making the proteins for us. That's also led to a collaboration on bioprocessing with fungi and green fluorescent protein in Brazil and Portugal. And then it goes from proteins to looking at cells. So, you know, larger biological tissue and so on. And from that, that leads to our cryopreservation. And each one of these are different projects that either a student of mine is working on or that I'm working on with someone else in their group. And side to understanding our proteins, we then needed to know more about, well, what's this happening between our liquid salt and water, and understanding those interactions. So that's led to other collaborations, particularly with groups in France and New Zealand, and just how we make the ionic liquids, and then going, well, okay, we can do this experimentally, but we need some models on the computer to really go, you know, what is the energy difference between this bond and this bond? So we're now trying to work out ways to develop computational models, and we're doing that with experts in France. And then we're getting lots of data, so we're bringing in our machine learning, and that's whole new project areas. And then we have some side projects looking at corrosion, because that's interesting. And I like having lots of different fun projects. I think, oh yes, and then even more recently, we're looking at developing whole new techniques around protein crystallization and using absolutely state-of-the-art X-ray laser facilities in Germany, and come with completely different approaches for how we can characterize tiny, tiny protein crystals. So as I mentioned on the last slide, it's not just my research group. This research involves many different people. So on the left, it's the main people involved at RMIT, involving other academics, my students, postdocs, and I'm hoping I haven't missed anyone out. I work very closely, a lot of this research with the beam staff at the Australian synchrotron for the SAX-WAX beam line. And the collaborators are all around the world. And these are the research leads for these collaborations, and some are at Australian institutes and others overseas. But for each of them, they then have their research group with their postdocs and PhD students. So thank you for watching, and I hope it's given you an idea of what I do as a researcher and how I got here.
Thanks for sharing your journey with us, Tam.
No probs.
From what I can understand, you're quite naturally drawn to research, but if I could go back now to your high school days where you mentioned you did quite well, was there a role model in high school that made you excited about science?
Not really. Out there, I had science teachers who helped me enjoy science, and particularly classes which had lab work. I really liked doing the demonstrations, and I had one moderately crazy physics teacher at high school, and I really remember his demonstrations because it was things like, to learn about step-up transformers, he got the whole class and electrocuted us. It kind of sticks with you. So it's comparing what happens before and after a step-up transformer. And there were a variety of different things, and things that we had to use the equations to predict where a ball would fall when it went down a ramp, and he put prizes up. So it was a sort of an interesting way to learn and apply it. Also come from a family where there is a lot of people in technical fields. So my mum was a maths teacher. My dad was very hands-on with making things. So I think all of that helps as well, and just a supportive environment. But no specific role models, but it also meant that I had no real idea what a career in research involved.
So it's great to see that you can collaborate and work with so many people, not only in Australia, but also around the world. And you mentioned about how it's a community that sort of inspires you to do different things. But what inspires you to continue to do research in this field?
So to get here, I think it was just kind of, in a way, incremental, but I kept enjoying it, so I kept wanting to do it. And it's really fun to be able to think of a question to particularly to solve significant problems which can have an environmental effect, and ways to replace petrochemicals, ways to make reactions greener. That's great. And I love working with people that have these real world problems and using my fundamental knowledge. But I particularly like asking these really fundamental questions and going, what happens? And then working out ways to solve it. So I love the problem solving, and I really love helping mentor and train up new PhD students and new research students. So helping them to develop the skills and help them to go from having done high school and undergraduate pracs where you're like, yep, okay, I'm following the lab manual, I get my answer, I check it. And for them to go to that next moment of there's usually a point where they go, okay, how do I check my answer? And you're like, well, no one's ever done it before. You've got to convince me that what you've come up with is right. And so just training people so that they can then go into their science career. There's just so many questions out there, and it's really fun, and getting to use big facilities like the Australian synchrotron and learning new techniques and working with other people.
Tam, you mentioned about those soft skills or enterprise skills, as we say at the tech school, as an important thing in science communication. And these are not always explicitly taught. How did you develop these skills beyond the lab to help you with your career pathway?
Yeah, it's a really good question. And there's such vital skills, well, probably not just for scientists, but also for scientists. And I think they are often overlooked and left to students to figure out for themselves. So I'm at RMIT, and I am really, really happy that we have a lot of project-based learning. So that students come in, have to work with others on a whole range of different things. And sometimes it's directly on a science project or on a planning for a project, but it involves them having to take on these roles and communicate and work together and be accountable to each other for the project's success. For me, how do I develop the skills? Well, I was definitely never formally taught them, and not a huge amount of project work as I went through university. So for collaborations, I always like working with other people. I think that sharing of ideas is just, that's great. I also like working on my own projects, but sometimes you don't have all the skills. So it's good to be able to bounce ideas and learn from others. I also like talking to people and asking what they're working on and seeing, hey, what could we do together? A lot of that comes with being in research longer and longer, so you have more confidence to walk up to the expert in some other area and go, hey, what do you do? Do you want to try this? Sometimes they'll look at you like you're crazy, and other times they'll be like, yeah, sure, okay. So it's sort of getting to the point of being willing to do that. So the communication is also what I've had to work on. So it's gone from me being by nature quite an introvert and feeling way out of my depth I'm surrounded by experts and always having that feeling that everyone knows more than me and what are you doing, to go, okay, they're just people, go talk to them. You might be in a room where you don't know anyone. Well, find some people, start talking to them. Find people who are extroverts, because then they'll always carry the conversation. Things like that, good survival methods. And it's like anything else. It's like learning the maths or the physics equations. They're skills. So the more that you actively go, well, I need to improve my communication, or I need to improve how I network with people, it's recognizing that they are skills that you can work on and improve, and not just go, well, I'm not good at it, or that person's good at that and I'm not. It's go, okay, well, I can improve. I can see it as something valuable that I have to also develop. And that's kind of the approach that I took. And sometimes it's going way outside the comfort zone and go, yeah, okay, I'll do this. And then regretting it, and then doing it and go, actually, that was awesome. Getting to lecture. So while I was at CSIRO, I was far more nervous about doing presentations because it only happened a few times a year. But now with the lecturing, you know, you're teaching to classes of up to 200 students and frequently, and it's like with anything else, the more you do it, the more it just becomes routine. You go, okay, yep, about to take a class of 200 students, should be fine. So then you're doing that, you're doing the conference presentations, you just get better at it. Also, lots of planning. What was the other? So the other part is the critical thinking, and that part of it as well, with that learning all the soft skills, learning the interactions. And I think it's something we need to teach a lot more of is in science and in the training, because we have, as I mentioned in the presentation, we get trained from high school and undergraduate that we're given, for most times, we're given our practical to work through, and we follow our steps and we get our answer and we check whether we got the answer. But the critical thinking, I think, really comes into it when you don't get that answer, when you have to get to the end and convince yourself that what you've done is right. And obviously to be able to convince others as well, but to look at it and go, well, I've got this answer. Could something else have happened that's affected it? Could there be some other variable that's affecting it? Could it be that I've stuffed up the experiments? And I think a lot of that comes just with experience. And I think the more different techniques you learn and the more experiments you do, you become aware that sometimes things don't work. And you have to be aware of, well, being able to look and go, do I believe this data? Can I convince myself? What other technique do I need to do? What controls and other things can I add in there to go, yep, there's no other possibility. It is what you think it is. And I think it's important to sort of have that more project-based learning to get those skills early on, but to also accept that some of that will just come with time.
From what you've mentioned today, everything you have done sounds so fascinating, whether that's getting to travel around the world to work with different scientists or mentoring PhD students or honours students. But I guess, what is the most fascinating thing you have come across in your career? What has been a wow moment for you?
Oh, wow moment. I think asking a scientist that, it's a bit like asking to choose their favourite child. I love all my projects. I don't think I have that many wow moments as the typical, like what you see in the movie of, oh, I've discovered such and such. I think my wow moments were at the start, where it's like sitting around often with the students and me going, hey, let's try such and such. And you know, we had one of those discussions just earlier today with the students. So we had one experiment, it's worked really well. I'm like, okay, I think for the next experiment, we should try doing this. And then might be able to learn such and such. And it's, you know, maybe a half-hour discussion setting out the research question that we're then going to explore. And we're both really excited about the possibilities of what we can do. I think that's almost more of the wow moment of going, here's the potential, because it's then followed by maybe 1 to 2 years of just hard work. And there's lots of what I'll call like mini wow moments of, we made the first sample, we got the first data, we got something we believe, and it's these little tiny milestones. But I think the wow's at the start. And my field, it doesn't tend to be lots and lots of stuff and then one final answer. It's lots of slowly, methodically collecting data, which doesn't sound as exciting, but they're still like cool little mini wow moments. But there have been a couple, I guess. So the first time I was able to get like a protein structure from the small angle X-ray scattering data and go, I can actually see tiny changes in something that's, you know, a millionth of a millimeter, and be able to see that it's changed, you know, just unfolded just a little bit and so on. Getting that sort of information, I love data analysis, so that was extremely exciting. And also getting the robot when it first started working in the lab after, you know, a year or two of designing it and just even figuring out how to get into the building. Yeah, lots of mini wows, and also just, you know, seeing PhD students taking ownership of their projects and their little wows as well as we go along. So yeah, no overall wows.
No, it sounds really great, Tam, and I think I like the thought of mini wows. So big wow, but lots of mini wows, and I think you're going to continue to get those mini wows, which is really exciting. And it's really exciting to see what you come up with in the future in your future research. So thank you again for joining us on the very first Optimism in Innovation talk. in the Bendigo Invention and Innovation Festival. Yeah, thank you again.
Thanks very much for the invitation. I hope the whole conference, I think it goes really well. Thanks.
Thank you.
Thanks, Tam.